Welcome friends. We have entered into summer of 2020. The season of summer is nostalgic to all of us. As we walk down the memory lane, it takes us to grandma's mouth-watering and tempting mango pickles. Have you ever thought what prohibits the mangoes in the pickles from getting rotten even when they are kept for a longer period? Again, the advent of summer is disgusting because of scorching heat. The scorching heat of summer drains our energy and we get tired easily. As a result, our body requires extra hydration and nutrition such as proteins, minerals, and vitamins. We know that dry fruits such as raisins and nuts are storehouse of powerful nutrients which when consumed refresh us and boost our energy level. You must have observed that these raisins when soaked in water overnight swell up in the morning. And same is the case with Bengal gram. They all swell when soaked in water. Now, what is the underlying principle behind this swelling phenomenon? Furthermore, in summer, when you come out from the AC room, the sudden change in temperature may cause sore throat. In such case, we are recommended a common home remedy to gargle with salt water. Salt water cures our sore throat and gives us relief. Have you ever thought why gargling with salt water relieves us from our sore throat? Moreover, summer brings some disruptions due to severe drinking water crisis. Have you ever pondered, despite being adjacent to sea, why even the coastal areas suffer from severe scarcity of drinking water? Can you figure out why seawater is not fit for drinking and how seawater can be made suitable for drinking? All these examples from our daily life that has been cited govern an important phenomenon called osmosis. And today our topic of discussion is osmotic pressure, which happens to be the fourth and last colligative property. Let us discuss the experimental setup to illustrate the process of osmosis and understand the concept of osmotic pressure. The apparatus consists of a chamber divided into two compartments by a semi-permeable membrane. Now, what is semi-permeable membrane? A membrane which allows the passage of only solvent molecules and not of solute molecules is called a semi-permeable membrane. Vegetable membranes and animal membranes are the natural membranes of this type. They may also be prepared artificially. Chemical semi-permeable membranes include cellophane, freshly prepared inorganic substances such as copper ferrocyanide, etc. The right-hand side compartment is filled with pure solvent and the blue sphere represents the solvent molecules. The left-hand side of the compartment is filled with solution, and this solution is prepared by adding non-volatile solute to the same solvent. Here, the red-colored sphere represents the solute molecules. The solution is fitted with a movable piston. This is the experimental setup. Now, in this setup, the phenomenon of osmosis will start. That is, the solvent molecules will spontaneously flow from pure solvent side to the solution side through the semi-permeable membrane. Can you see how the solvent molecules represented with blue sphere are moving from the pure solvent side to the solution side, and the semi-permeable membrane is restricting the movement of the solute molecules, but it is allowing the movement of the solvent molecules. This process of osmosis will push the piston on the left hand side upward. This upward movement of the piston can be prevented by applying extra external pressure on the piston to keep it in the original position. This excess pressure required on the solution side just to prevent the process of osmosis is termed as osmotic pressure, and it is designated as pi. This concept of pi sets the situation in equilibrium. So, the mechanical pressure that must be applied on the solution side in order to prevent the process of osmosis is termed as osmotic pressure of the solution. Now let me define osmosis and osmotic pressure once again. What is osmosis? The spontaneous flow of solvent molecules from pure solvent side to solution side when both are separated by a semi-permeable membrane is termed as osmosis. We can also define osmosis as the spontaneous flow of solvent molecules from a dilute solution to a concentrated solution when the solutions are separated by a semi-permeable membrane. In osmosis, the solvent molecules move from low concentrated side to high concentrated side when both the solutions are separated by a semi-permeable membrane. Remember, here low concentrated and high concentrated is with reference to solute molecules. Now, what is osmotic pressure? The excess pressure required on the solution side just to prevent the process of osmosis is termed as osmotic pressure. Always remember that the osmotic pressure is brought into existence only when the solution is separated from the solvent by a semi-permeable membrane. Osmotic pressure is a hydrostatic pressure that just prevents or checks the process of osmosis. Now, what will happen if the pressure applied on the solution side is greater than osmotic pressure of the solution? In this case, the solvent will flow from the solution side to the pure solvent side when they are separated by a semi-permeable membrane. Or we can also say that the solvent will move from concentrated solution to dilute solution. This is known as reverse osmosis. So let us define reverse osmosis. When the pressure applied on the solution is greater than the osmotic pressure of the solution, the solvent starts flowing from solution into the solvent through the semi-permeable membrane. This phenomenon is termed as reverse osmosis. This phenomenon of reverse osmosis had been found very useful for the desalination or purification of brackish or seawater. Now, seawater contains many dissolved salts and is more concentrated as compared to the fresh water. In order to purify seawater, it is kept in contact with pure water through a semi-permeable membrane. On applying external pressure greater than the osmotic pressure to seawater, reverse osmosis takes place. Water, that is solvent, will be forced to flow from seawater side to freshwater side, leaving behind the dissolved salts. This is the way in which seawater is purified. So, in the desalination of seawater, we are using reverse osmosis. Now we will study laws of osmotic pressure and Van 't Hoff's equation. Based on the experimental observations, Van 't Hoff formulated the following empirical relations which are known as Van 't Hoff's law. The first law, at constant temperature, the osmotic pressure of a dilute solution is directly proportional to its molar concentration. That is, pi by C is constant. Second law, at constant concentration, the osmotic pressure pi of a dilute solution is directly proportional to its absolute temperature. That means pi by T is constant. Now combining the above two laws, we get pi directly proportional to C into T. That is, pi is equal to CRT, where R is the proportionality constant and has the same numerical value and significance as the universal gas constant. Now pi is equal to CRT. Now the C, we are replacing it with N2 by V, where N2 is the number of moles of the non-volatile solute, which is dissolved in V liters of the solution. So pi is equal to N2 by VRT. That is, pi into V is equal to N2RT. This equation is known as Van 't Hoff's equation. Now this equation, pi V is equal to N2RT, that is Van 't Hoff's equation, clearly shows that osmotic pressure is a colligative property. And this osmotic pressure of a solution at a given temperature depends only on the concentration of the solute and is independent of the nature of the solute. So once again we can say that from Van 't Hoff's equation that pi, osmotic pressure, is a colligative property. Now this pi V is equal to N2RT and PV is equal to nRT, that is ideal gas equation. These two equations are analogous. So seeing the term by term similarity between the osmotic pressure equation, that is Van 't Hoff's equation, and PV is equal to nRT, ideal gas equation, Van 't Hoff proposed that the behavior of the solute molecules in a dilute solution is exactly identical with the behavior of the gas molecules in the gas assembly. Osmotic pressure, being a colligative property, is a very good method for determination of molecular weight of a solute. The osmotic pressure of a dilute solution of a non-volatile solute is given by pi is equal to CRT, where pi is the osmotic pressure, C is the molar concentration, R universal gas constant, and T is the absolute temperature. This is equal to N2RT by V, since C is equal to N2 by V. Now this N2, that is number of moles of the non-volatile solute is equal to W2 by M2. What is this W2? W2 is the amount of the non-volatile solute and M2 is the molecular weight of the solute. So this N2RT by V is equal to W2RT divided by M2 into V. Now rearranging, we get M2 is equal to W2RT divided by pi into V. Thus, molecular mass of the solute can be calculated with this equation, provided the osmotic pressure pi of the solution, mass W2 of the solute dissolved in V liters of the solution, and temperature T are known. The value of R is taken to be equal to 0.0821 liter atmosphere per Kelvin per mole when pi is expressed in atmosphere, volume in liters, and T in Kelvin. Now this measurement of osmotic pressure is a suitable method for the determination of molecular mass of proteins, polymers, and macromolecules. Now, what are the reasons? The first one, biomolecules like proteins are not stable and they break down at high temperature. Therefore, elevation in boiling point, that is delta TB, is not appropriate for the determination of molecular masses of biomolecules. But osmotic pressure can be measured at room temperature. The second point, as the molecular mass of the biomolecules are high, so change in delta T, this delta T can be either delta TB or it can be delta TF. They are very small. Now, what is the connection between high molar mass and small value of delta T? We know that delta TB, delta TF, they are all colligative properties. And colligative properties are always inversely proportional to their molar mass. So, if the biomolecules, they have high molar mass, their delta T will be very small. So, delta T for their solutions being very small, it becomes very difficult to measure their molecular weight accurately. But osmotic pressure of such solutions is of the order of 10 to the power minus 3 atmosphere and can be determined easily. So, osmotic pressure measurement is the best method for the determination of molecular mass of proteins, polymers, and other macromolecules. Now let us discuss one numerical based on osmotic pressure. Calculate the osmotic pressure of an urea solution at 27 degrees centigrade, which contains 6 gram of urea dissolved in 100 milliliter solution. Now urea is our solute here. So this is the structural formula of urea. From here, let us calculate its molecular weight. So the atomic mass of nitrogen is 14, hydrogen 1, carbon 12, oxygen 16. So molecular weight of urea is equal to 14 into 2. Why 14 into 2? Because we have 2 nitrogen. Plus 4 into 1. How many hydrogen we have here? We have 4 hydrogen, so 4 into 1. Plus 12. This 12 is for carbon. Plus 16. 16 for oxygen. So the sum comes out to be 60. So the molecular weight of urea is 60 gram per mole. W2, that is weight of urea, is 6 gram given in the problem. R, universal gas constant, is equal to, we have taken it to be 0.082 liter atmosphere per Kelvin per mole. Now, since you have taken R in liter atmosphere, so V, that is given 100 ml, we will convert it to liter. So V is equal to 100 ml is equal to 100 by 1000 is equal to 0.1 liter. Now we know this equation, pi V is equal to W2 by M2 RT. Rearranging, we get pi is equal to W2 RT divided by M2 into V. Now we will put all the values of W2, M2, V, RT, and we get pi is equal to 24.6 atmosphere. The occurrence of osmosis can explain many natural phenomena of our daily life. To understand these applications, let us study isotonic, hypertonic, and hypotonic solutions. Now, what do you mean by isotonic solutions? Two solutions having the same osmotic pressure is termed as isotonic solution. Pi 1 is the osmotic pressure of solution 1 and pi 2 is the osmotic pressure of solution 2. At a given temperature, if pi 1 is equal to pi 2, then the solution is termed as isotonic. Now, if pi 1 is equal to pi 2, then according to Van 't Hoff's equation, we know that pi is equal to CRT. So, pi 1 is equal to C1RT and pi 2 is equal to C2RT. Since pi 1 is equal to pi 2, so C1RT is equal to C2RT. RT will cancel, hence we will get C1 is equal to C2. So we can conclude that isotonic solutions have equal concentrations at same temperature. Now, suppose if pi 1 is greater than pi 2, then it will imply that C1 is greater than C2. So, if two solutions whose concentration varies are separated by a semi-permeable membrane, then if solution 1 has higher osmotic pressure, that is higher concentration than solution 2, then solution 1 will be termed as hypertonic solution and solution 2 will be termed as hypotonic solution. So once again I am repeating this. If two solutions have unequal osmotic pressures, the more concentrated solution is said to be hypertonic and the more dilute solution is described as hypotonic. Now suppose if hypotonic and hypertonic solutions are separated by a semi-permeable membrane, can we say or can we tell that in which direction osmosis will take place? Now, hypotonic solution is dilute solution and hypertonic is concentrated solution. We have learned that osmosis is a spontaneous flow of solvent molecules from a dilute solution to a concentrated solution when they are separated by a semi-permeable membrane. So, in this case, osmosis will take place from hypotonic solution to hypertonic solution. That means the solvent molecules will move from hypotonic solution to hypertonic solution. Now let us understand some of the applications of this osmosis in our daily life. To study the contents of red blood cells which are protected by a semi-permeable membrane, a technique called hemolysis is used. The red blood cells are placed in a hypotonic solution when water moves into the cells. The cells swell and eventually burst, releasing the hemoglobin and other molecules. Similarly, when resins are placed in water, that is hypotonic solution, they absorb water by osmosis and swell up. We know that resins from inside, they are concentrated, so water flows from outside into inside of the resins. Similar is the case of Bengal gram, peanuts, etc. Now let us discuss hypertonic solutions. When a bacterial cell is placed in a hypertonic solution, the intracellular water tends to move out of the cell by osmosis. This causes the cell to shrink. Similarly, while preparing mango pickle, salt is added to the mangoes. So mangoes are exposed to a hypertonic solution. Hence, water from the mangoes comes out, and this helps to prevent the inclusion of bacteria. Similarly, gargling with salt water is advised in case of a sore throat. This is because by use of hypertonic salt solution, the extra water accumulated in the sore throat comes out with the saline water through osmosis. So these are the few applications of osmosis. Today we have discussed our last colligative property, osmotic pressure. In our next class, we will study abnormal molar mass and Van 't Hoff's I factor, which is a ratio of observed value of colligative property to the normal value of colligative property. Thank you and have a nice day.